Hello, everyone. How's it going? Pretty tired? Is this showing? All right, cool. So thanks for being here. My name is Stephen Pu. I'm one of the co-founders of the Taraxa project. Today, we're going to present something a little bit more fun, okay? The title looks very boring. Resource efficiency of realized mainnet throughput of layer 1s. What it really is a study that seeks to expose the lies that you've been told about layer 1 performance metrics. All right, let's get to it. So the layer 1 space, the Web3 infrastructure space has been getting extremely crowded, increasingly more so every single year. And the need to differentiate between those infrastructure networks has been growing. But that need has not been fulfilled. It's been thwarted by unrealizable theoretical performance metrics, unverifiable tests done on secret networks, overly optimistic assumptions that people are making while conducting these tests, and of course, juicing up their performance with supercomputing level hardware. All right? So how do we fix this? How do we cut through the hype? How do we cut through the lies and the BS? Well, first of all, you conduct all your tests on Mainnet. You only trust realized performance metrics on Mainnet. It's on Mainnet or it didn't happen, okay? Mainnet or it didn't happen. This gets rid of the theoretical numbers. This gets rid of the secret, non-transparent, unverifiable numbers, okay? This gets rid of the unrealistic, non-real world assumptions. Have your performance metrics on Mainnet. Second, the metric must be balanced by hardware costs so that you're not artificially juicing up your numbers while you're conducting performance tests. There are different types of performance, there are types of consensus, such as leader-based consensus mechanisms that especially exploit juiced up hardware. You guys all know what I'm talking about, probably. A lot of networks out there with minimum requirements of their validator nodes that are extremely expensive. Might as well be a supercomputer. So we propose a new metric. Very simple, right? So simple, even my grandmother understands it, all right? It is simply TPS per dollar spent. So we take two numbers, realized TPS on Mainnet, divided by the cost of one single validator node, right? That's it. Very simple. Everyone can understand this, right? It cuts through a lot of the lies. The sources, right? We get the throughput on the Mainnet sources primarily for this study through a website, an application called ChainSpec, which is an application that's dedicated to benchmarking on-chain performance across Web3 infrastructure networks, layer 1s and layer 2s. Go check it out. Very interesting. We get the hardware costs, configurations from every single project's their own official documents. We didn't make it up. Their own official documentations, their minimum hardware requirement for their validator nodes, and we estimate the cost using the Google Cloud calculator, right? All perfectly transparent. Every piece of data in this study is on taraxa.io/fast/data. There's a Google sheet. Every single bit of data is sourced. Go check it out. You can reproduce it if you want. If you have a problem with any of the data, let us know. Happy to correct it if we made a mistake. All right? Let's go through and see how this is done. Number one, we look at realized throughput on Mainnet. So on ChainSpec, if you go through and sort by maximum TPS realized on Mainnet across a 100-block range, you get 34 chains up and including Ethereum, okay? We only included 22 in our study. We excluded 12, 10 of which are permission networks. So permission networks, right? Beyond, besides being a complete heresy in the world of decentralization, they have highly relaxed trust models and highly relaxed networking condition assumptions. So their performance numbers are not technically comparable to permissionless networks. The other one is sharded networks. Now, sharded networks, sharding is a perfectly fine way to scale. It just so happens if you actually add up all the throughput numbers across sharded states, that is not a fair comparison because you're trading off cross-shard transactional latency for expanded storage and throughput and storage. If they're not sharing the same state, it's not a fair comparison, okay? So out of the 34 on chain spec, sorted by max TPS realized on chain, 12 were excluded, 10 because they're permissioned. They shouldn't even be on that dashboard as far as I'm concerned. All the layer 2s are permissioned, by the way, in case anyone doesn't know. And 2 were excluded because they were sharded. So we're only going to look at the 22 networks. And here are copied directly from chain spec, the 22 networks, maximum realized TPS on chain, right, across an 100 block range, right? Copy directly from their website. You can go look at it yourself too, right? There's another number, the number that we're all very familiar with, theoretical TPS, right? Sounds really great. You know, anyone can say anything about theoretical. I can say that Taraxa has a theoretical TPS of infinity. You know, whatever, not verifiable, right? So projects are provided their theoretical TPS on chain spec as well. And look at the difference between the theoretical TPS and the actual realized TPS. It's pretty big, right? We put a bullshit number on there too. Yeah, look, 10 for Taraxa. Others are much more ambitious than we are. On average, of the 22 networks that are included in the study, there's a 20x gap between theoretical TPS and actual realized on-chain mainnet TPS. 20x, right? And let's plot, right, on the horizontal axis, maximum observed TPS actually realized on mainnet versus theoretical TPS, right? So group A, modest TPS, modest aspirations. They're very honest. They're honest people, right? Great. Kudos to the honest people. Group B, pretty good TPS, modest aspirations in their theoretical estimations, also pretty good. Group C, I can only describe them as very ambitious. Crap on-chain TPS, very ambitious aspirations, okay? So you guys can check out who these guys are by looking at the source data at taraxa.io/fast-data. Look at the numbers yourself. All right, we talked about max on-chain TPS. That's the denominator. Let's look at the numerator. The numerator is cost per month for a single validator node. Where did we get this from? We got it from every single project's official documentation. You go on taraxa.io/fast-data, every single documentation page where we got these configurations are linked. Check it yourself, right? Here are the hardware configurations by CPU, memory, and hard drive, right? So these were adjusted slightly, scaled slightly, so they fit nicely onto the graphic. At the top, the least hardware requirement for CPU, 8 gigs for memory, and 100 gigabytes of SSD, right? This is for a pruned light node for Taraxa, pruned consensus light node. Much bigger one at the bottom, right? This is just for reference. So once we get the hardware configurations, the minimum hardware configuration for a validator node from every project's official documentation, we turn them into numbers. We turn them into dollars by putting them into Google Cloud Calculator. Now, the absolute numbers that you're getting out of the Google Cloud Calculator is not important. What is important are the relative numbers. We're talking about ratios. It's very important that all the data come from the same source. Everyone knows Google Cloud is not the cheapest, but we're getting it from a consistent source, okay? Every single Google Cloud configurations where we got the dollar numbers are, again, any guess where it is? Taraxa.io/fast-data. Every one of them linked. Click it into yourself, see it for yourself, all right? So here are all the numbers copied down for every single hardware configuration for minimum hardware requirement for a validator node across these 22 networks. This is the dollar amounts. Again, the absolute numbers are not important. It's the relative numbers that are important. We're calculating a ratio here, okay? And here's the result, right? TPS per dollar spent. Or the longer version, mainnet realized TPS. Realized, not theoretical, not made up, not dreamed up. Realized mainnet TPS per dollar spent per month for a minimum hardware requirements for a single validator node, okay? These are the results. Check it out yourself. Taraxa on its own right now has a mainnet maximum TPS, realized TPS of 4906. The Google Cloud estimator calculates our validator node costing 98.7, just under $100 per month. And we have a ratio of 49.7. So making us #1 in the world in terms of TPS per dollar. These are real numbers, transparent, verifiable, not theoretical, not dreamt up, all right? If you'd like to disagree, love to understand why, okay? I don't understand why no one does this, all right? So, if you're still awake, you might ask, how did we achieve such performance? I know there was no shilling. I'm just talking about our technology. So, Taraxa achieved this level of performance and efficiency because of the following reasons, right? Number one, we have a next generation block DAG architecture. So block DAG, if you haven't heard of it, it was first described in a paper called Phantom Ghost DAG in 2018 by Sompolnitsky, Wyborski, and Zohar. It's a very interesting architecture. We read the paper, we implemented it. It allows parallel addition of blocks onto the network instead of single chain, all right? So on a single chain, you can only add one block at a time. On a block DAG, you can add multiple blocks at a time, all right? Almost every single mainstream layer 1 you see today are single chain architectures. They're massively sacrificing security guarantees to get the performance that they're getting. Massively. Leader-based consensus, all right? That's a great example. They predict pre-compute all the leaders that are going to be producing the blocks. And every single leader stay there, producing blocks for many, many epochs, right? Let's turn an entire network of thousands of nodes, attack surface of thousands of nodes, let's turn into a single node, right? Great sacrifice of security for performance. Block DAG doesn't have this issue. It doesn't need to sacrifice security or decentralization to achieve this kind of performance. And this is borne out by realized mainnet TPS, not dreamed up theoretical paper TPS, all right? Second, we have a dynamic sub-second block rate. It makes sure that the network does not waste any work. It tunes up the block production rate when it sees there's a drop in the transaction overlap between the DAG blocks. And it turns it down when network traffic goes down the other way. We have VRF and VDF, which reproduces the random delay in proof-of-work systems without the arms race of proof-of-work systems that cost a lot of energy. It has all the benefits and none of the downsides. We have true finality with an asynchronous PBFT process. This is very critical. Anyone who has tried to take an EVM and push it above 100 TPS will realize that the EVM actually puts all reads and writes into state through the Patricia-Merkle tree first. How do you get past that? Why did they do that? Well, it's because they're accounting for state reversion risk. So in order to get rid of state reversion risk that's inherent in probabilistic finality, you have to introduce true finality. So we introduced an entire layer of true finality in order to remove the need to always go through the Patricia-Merkle tree every single time state is read and written into, okay? We have asynchronous and parallel execution, and of course, we're 100% EVM compatible, right? This is ETHDenver, show up with EVM compatible layer 1s, right? We wouldn't dare showing up with some Rust VMs. All right, so Taraxa this year has 5 bounties as part of the hackathon. So we hope that after this talk, if you're not too angry and too pissed at me, you will like to check us out. You would like to build on the fastest and most efficient layer 1 in the world. We have 3 AI agent bounties, and that's very unique, right? Everyone has AI agent bounties. I hear the word AI every 3 seconds sitting at the desk. What's unique about Taraxa is that we have a platform called Chape built on top of the layer 1 that actually is a decentralized network that feeds real-time Telegram conversational data from public Telegram groups, from over 20,000 crypto English-speaking public Telegram groups. No one else in the world gives you this data. Nobody else. I looked very hard. That's why we built this. And this is what's going to make the agents that are built on this unique data set substantially different than all the other agents, right? L1s, they're easy. Download the model, feed it some data. Depends on what kind of data you're feeding it. This unique data set gives you unique insights, okay? Check it out. You won't be disappointed. We also have 2 other infrastructural layer 1 bounties for you to check out. But come to Taraxa.io on our front page are all the resources you need to check out our bounties. All right. Our team is sitting at desk T1 over there. All right. And we have a booth 314. If you agree with us, if you disagree with us, if you want to yell at me, come to these places. I'd love to talk to you. All right? Thank you very much. Across gas